Welcome back. In this video, we're going to look at polar coordinates in the complex plane. Much of this will be a review for you. Since the complex plane is just the xy plane, polar coordinates in the complex plane are exactly the same as polar coordinates in the xy plane. What may be new is the arithmetic. Since we can multiply and divide complex numbers, we'll be able to see how that works in polar coordinates. Let's get started. We have our usual complex number z, which is x plus jy. I've plotted that already over here in my complex plane. Now, we construct this right triangle with legs x and y and the hypotenuse going from the origin to z. And then our polar coordinates are the length of that hypotenuse r, that is the distance from z to the origin, and theta, the angle that that hypotenuse makes with the positive x-axis. So let's write that over here. R equals the distance of z to the origin. I'll just write z to O. And theta equals the angle to the positive x-axis. I'll abbreviate positive x-axis. Now there are many names for these things, so let's give those first. Here's terminology and notation. R is often written as the absolute value of z, and that's read as the magnitude of z. It's also the modulus, again, of z. It's the norm of z, or it's the length of z. Mostly we'll call it the magnitude here, but it's often called any of these other terms. Then there's theta. Theta is denoted as angle z. It's also denoted as arg of z. And this is read as the phase of z, or the argument of z, or simply the angle of z. Let's finish this slide by writing down the formulas relating r, theta, and x and y. So we can see from the triangle and the Pythagorean theorem that r equals the square root of x squared plus y squared. We can also see that theta, the tangent of theta, is opposite over adjacent, which is y over x. So theta is the inverse tangent, which I'll write as tan inverse of y over x. Going the other way, it's easy to see that x equals r cosine theta. That's simply saying that the cosine of theta is the adjacent over the hypotenuse, or x over r, and likewise we have y equals r sine of theta. On the next slide, we'll get some practice with these. Let me highlight these formulas and this picture. That's polar coordinates in a nutshell. You should know it perfectly. Here I've prepared the slide with 4 different complex numbers. We'll plot them all in the plane and figure out their polar coordinates. Let's just start at the top. We have 1 plus j. 1 plus j tells us to go out 1 along the x-axis and up 1 along the y-axis. And we get right there at 1 plus j. Then either algebraically or from the triangle here, we get that the length, the distance from this complex number to the origin, is square root of 1 squared plus 1 squared, or square root of 2. And the angle right here is clearly 45 degrees, or pi over 4 radians. Next one, 1 minus j, that says go out 1 along the x-axis, but then down 1 unit in the y direction. Here we have this. Angle is clearly minus pi over 4, and the length again is square root of 2. Square root of 1 squared plus 1 squared. Square root of 2. What about z equals 2? If we go out, the real number 2 says just go 2 units along the x-axis. So its length is 2, and its angle is 0. Finally, we have our last number, j. J is plotted right here at 1 on the y-axis. That's j. And so the polar angle, written like that, is pi over 2. And the magnitude, your 1 unit from the origin along the y-axis, is just 1. Let's go in the other direction. If I choose a different color, if I give an r equals 2 and a polar angle of minus pi over 2, I can do this geometrically. I can go down pi over 2 radians below the x-axis because it's negative pi over 2 radians, and then that gets me to the negative y-axis, and I have to go down 2 units. So here's minus 2. That's my point, which is minus 2j. So I can put that right here, minus 2j. I could have done it the other way. In all cases, I could have done these all using just the algebra. For instance, the length of 1 plus j equals square root of 1 plus 1 equals the square root of 2. And the argument, or the angle of 1 plus j, equals the tan inverse. The coefficient of j is 1 over 1, which is the tan inverse of 1, which we know is pi over 4. Or for this right here, where we were given the polar coordinates, we could find the rectangular coordinates using the formula x equals r cosine theta. R was 2, and theta was minus pi over 2. Cosine of minus pi over 2 is 0. Likewise, y equals r sine theta. R again was 2, and theta was minus pi over 2. Sine of minus pi over 2 is minus 1, so I get minus 2. Then our complex number z, which is x plus jy, just equals x equals 0, y is minus 2, so we get minus 2j as above.